So, good evening, everyone. My name is Kostas Stasis. Happy New Year. This is the first colloquium of the Hellenic Astronomical Society of 2021. And on behalf of the Governing Council, I would like to introduce Professor Rigopoulou. Dimitra Rigopoulou was born in the picturesque city of Volos and studied physics at the University of Ioannina. She obtained her PhD in 1995 from Queen's Mary, University of London, under the supervision of Andy Lawrence. She then moved to the Max Planck Institute for Extraterrestrial Physics to work in the infrared astrophysics group of Professor Ayhan Genzel, who was awarded the Nobel Prize in Physics in 2020, last year. Then she moved as a faculty to the Oxford University, where she is currently a professor of astrophysics. Over the past 20 years, Professor Rigopoulou has made fundamental contributions in advancing our knowledge of luminous infrared galaxies using ground-based observations in near-infrared and sub-millimeter wavelengths, as well as spaceborne facilities like Spitzer and Hel.A.S. She's currently involved in a number of ALMA projects, and she's preparing to use the JWST, developing mid-infrared spectroscopic diagnostics based on the emission of polycyclic aromatic hydrocarbons, which I understand is also the topic of your colloquium today. So without further ado, Dimitra, the floor is yours.
Thank you, Kostas. Hello, everybody, and Happy New Year. It's a pleasure to give this talk. I wish I could be there in person, but circumstances are such that we have to give this colloquium online. Right, so as Kostas mentioned, and as you probably saw in the title of my talk and my abstract, I'm going to talk about polycyclic aromatic hydrocarbons from space, and what in particular can we learn from studying them? Okay, so here is a summary of what I will be talking about. So I will start with a sort of review, an overview of what we know so far on polycyclic aromatic hydrocarbons, going back to observations and results we had from ISO, the Infrared Space Observatory, which was the first infrared space mission from ESA. We'll talk about the role of PAHs in the interstellar medium. Then I will move on to what we know about PAHs in active galactic nuclei, which is also one of my sort of personal favorites. And I think there will be a lot that we can learn from JWST. And then I will spend the second half of the talk introducing the kind of work we have been doing here in Oxford on computing theoretical spectra of PAHs. What can we learn from those, and how can we connect our observations to this spectra? And then I will give my summary and outlook. This work is the effort of a big it's a collaborative effort, and I list here my collaborators, and all credit should go to them rather than myself. So Sir Dave Clary and Xiao San, it's my chemist colleagues. And then my group in Oxford, Ismael Buthena, Marie Fotis, and John and Pat Ross. My collaborators in Spain, Almudena and Miguel, Leslie Hunt in Archetri, Georgios and Isabella in Denmark. And I should also acknowledge support from the Oxford University Press, John Felfan. Okay, so why do we care about PAHs? And what are they actually, first of all? So PAHs, as you can read of the view graph, are a group of a number of, well, they form a family of organic molecules, which are made up of 2 or more benzene rings. Now on Earth, we know we have identified PAHs as the carcinogenic products of incomplete combustion, such as fossils. But in space, we use them, they're not dangerous as such, and we use them to identify unique and complex molecular molecules. It's a molecular inventory. We also use them, and that's mostly for astrobiology, but for sort of more mainstream astronomers, we use them as sensitive barometers of the local condition of the universe. And the purpose of my talk today is more towards how we use PAHs to infer the physical properties of the interstellar medium in our own galaxy and galaxies further away. Okay, so why should we care about PAHs? And where are they found, first of all? So the PAHs are grow on interstellar dust. And now interstellar dust is a very small fraction of the interstellar medium. As you know, this is the famous pie chart of the interstellar medium, where most of it, about 75% is made up of hydrogen, 25% is made up of helium, and a very small amount consists of the interstellar dust. Now, PAHs are part of interstellar dust because they need the grains to grow. So, as such, they are a very small fraction of what makes up the ISM, right? So, and when I had given a couple of years ago a similar talk in Italy at Arcetri, one of the audience said, well, they are little guys with very loud voice. And this is very much true. So the PAH family, although they're a small fraction of the ISM, they make their signature very well known in the spectra of galactic sources and extragalactic sources, as we will see later on. So this is why we care about PAHs. They are very good diagnostics of conditions in the ISM, but also possibly star formation in galactic and extragalactic sources. Now, how do PAHs are excited? So the PAH molecules are transiently heated by ultraviolet photons from the photosphere of newly formed stars. And they are predominantly, we think, associated with the photodissociation region. And in that cartoon, you can sort of see that the PAHs are sort of, they grow on the dust grains and they're mixed with the gas in photodissociation regions. They can account for quite a large fraction of the total infrared luminosity of galaxies, and the bottom two graphs, I've taken them from a talk by Jedi Smith, but I think they demonstrate convincingly why PAHs are important. So if you see on the left-hand side, you see the strength of other lines that we know, emission lines, such as the carbon-2, the H-alpha, the silicate oxygen lines, and what fraction of the total infrared luminosity of the galaxy they account for. And on the right-hand side, you can see that the 7.7 accounts for 4%, and if you add up all the features, the features at 7.7, 11.3, 6.2, 17, these are the strongest PAH features. There is a number of them, as I will show in a minute, but collectively, they can account for 10% of the total infrared luminosity in galaxies, which is quite a significant fraction if we take into account that, you know, sort of carbon-2 accounts for up to 25% and H-alpha even less than that. Right, so the first detection, I thought this is perhaps fitting to start from quite some time ago, from the first detection of PAHs in galaxies. Most of what I will show today refers to extragalactic detections of PAHs, and I do apologize to anyone of you in the audience who do galactic astronomy and have an interest in galactic PAHs. So this is the first detection of PAHs from Fred Gillett in 1975, and you can sort of see here at 11.3 a PAH in M82 and NGC 253. Later on, we have one of the first surveys of PAHs, which we did as part of the ISO program we had at MPE. And these are the first sort of, as I said, the first largest survey we had observed. We managed to observe PAHs for about 40 ULIRCs and 20 starbursts and AGNs back in with ISO. And then Reinhard Genzel used the strength of the 7.7 feature and fine structure lines to present this first diagnostic diagram of AGN and starbursts, which, with all the caveats on how we defined the continuum around the 7.7 micron feature, worked, I must say, worked relatively well. So this is how we started. Then with Spitzer, the sort of research into PAHs continued. And from the work of Hel.A.S Spitzer et al., you can see here that PAHs scale very well with the far infrared luminosity in galactic and extragalactic regions. And you can see here, these points represent galactic regions, and these are extragalactic starburst galaxies and normal galaxies. There is a sort of a good correlation spanning over a number, over a wide range in both luminosity and luminosity in the PAH. And this sort of formed the basis of using PAHs as tracers of star formation. Spitzer did a lot of, offered us the opportunity to understand PAHs a lot more and use them now as probes also of the condition of the ISM. And this is the well-known fork diagram of Henrik Spoon, where he combined the equivalent width of the 6.2 PAH feature with the silicate strength. This is the deep at about 9.8, which is due to silicon absorption in the line of sight towards a given galaxy. And what you can see, although this plot is sort of very busy and rather complex, but what I want you to take away from this is that it appears, and I think Henrik showed rather convincingly, that the galaxies are systematically distributed along these two branches. And this is why it was called the fork diagram. And one of these branches is the branch which contains the sort of the more deeply embedded obscured nuclei, which is more up on this branch. And then you start from the more embedded, and then you go towards the less embedded and the more starbursty objects. So basically, this separation on these two branches reflects this fundamental difference in the properties of the dust and in the geometry of the sources. Clumpy versus non-clumpy, obscuration versus less obscuration. So in particular for these ultraluminous infrared galaxies, for those of you who are a bit more familiar, you can see that ultraluminous infrared galaxies populate both of these two branches, which sort of reflects the very diverse nature of this class of galaxies. But I'm not going to go further into the properties of ultraluminous infrared galaxies, but stay more on the PAHs. Here on the left-hand side is again the same kind of plot, the Spoon plot, where again we look at the strength of the 6.2 feature. I should remind here again that the sort of the most prominent features are at 3.3, 6.2, 7.7, 8.6, 11.3, and there are some further out. And whereas with ISO, we looked primarily at the 7.7, with Spitzer, the focus was more on the 6.2 micron PAH feature. The plots on the right-hand side come from Miguel's work, and these are some of the very few spatially resolved sort of spectral maps which show the extent of the PAHs into higher luminous galaxies. Now, this is important because most of the spectra that we have for PAH emission are taken through a slit, and we lack information about the extent of the emission. And this is where we think a lot of new science will come with the James Webb, with the James Webb telescope, because it will afford a much better spatial resolution. So we can actually now use the PAHs, the diagnostic power of PAHs, in a spatially resolved manner. Okay, so we saw that PAHs can be used to trace star formation. We saw that they can also be used to trace the properties of the underlying source, obscuration, and maybe, as we will see now in the next slide, the properties of the dust grains. Now, here on the right-hand side, you can see the spectrum of just NGC 1365, but the reason why I show this is to show you the PAH bands, the PAH features, together with a number of fine structured mid-infrared lines, which one finds in the spectra of galaxies. Now on the left, this is again from the work of Sabina Stierwalds, using the work of Drain and Lee, and these are these black tracks that you can see here. They try to infer the properties of the dust grains. As I said, remember that PAHs grow on dust grains, so by studying them, we can also infer the properties of the grains in galaxies. And their result from diagnostic plots like this is that perhaps the AGNs, and these are the red points, the active galactic nuclei, their values are a lot more spread out, which means that the properties, they have different properties of grains. And we can also infer more about whether the grains are neutral or ionized. I won't go into more details now because I will come back to this kind of diagnostic plots later on. But this is just a sort of an overview of the various ways that PAHs have been used so far to infer properties of both the ISM, but of star formation in galaxies. Now, this is from the work of Xieh, 2018, where these authors noticed that whether you look at galactic sources, and these are the collection of spectra on the left-hand side, and in the middle of normal galaxies of low luminosity AGNs, there is a uniformity in the shape of the spectra. And this basically justifies the use of the PAH bands as tracers of star formation, basically, both in galactic and extragalactic, and also further out. In fact, from the works of Shipley and Sivai, they try to extend this use of the PAHs as tracers now of star formation rate. And as you can see here, there is a pretty good agreement. If you compare the luminosity, the total luminosity which comes out in the PAH features with the star formation rate as measured from H alpha at the top, or measured with H alpha and the 24 microns, so something luminosity that comes out in the infrared. And there is a bit, I mean, it depends on how accurate you want. Yes, there is a lot of scatter in these relations, but overall, over a wide range of luminosities, of orders of magnitude, the correlation exists. And from this kind of studies and correlations, we have now established that PAHs can actually be used to trace star formation rates in galaxies. But there's always a but in astronomy. We do know that metallicity or abundances influence the strength of the PAHs. Now, this is taken from the work of Drain in 2007, and the y-axis shows the PAH index. And this is, you can sort of simply take this as a measure of the strength of the PAHs as a function in the x-axis of metallicities, of abundances. And as you can see, that at low metallicities, this PAH index is low. So the strength of the PAHs we know is diminished. And this, of course, is a concern, right? Because if you want to take a PAH and measure star formation rate in galaxies in the early universe, you have to be careful, because we know that in the early universe, galaxies have lower metallicities, or for those that we have measured. So this is, again, something that is a concern when using PAHs. The plot here to the right is from the work of Leslie Hahn, where again she looked at the surface density of PAHs versus total infrared luminosity scaled, and abundances again, metallicity, and she notices the same. The blue points are dwarf galaxies, the green and red points are normal galaxies, and she notices as well this difference. So what I would like you to take out of this is that yes, the PAHs can be used as star formation rate indicators, but we always need to bear in mind their dependence on metallicities. And I will come back to this point later on when I show the models. Right, so what about PAHs now in the distant universe? I showed you all the slides and the results that I have shown so far are related to PAHs in nearby galaxies. Now here are two spectra, which I think are probably the highest redshift. The 4.55 is the highest redshift object where the PAH has been detected, and that's from Dominic Richer's work. And on the left-hand side is one of the growth strip galaxies that we detected with Spitzer back in 2008. Two very different sources where again we have detection of PAHs. So PAHs do exist at high redshift. That is for sure. And I think the James Webb will have the ability, I hope, to make a lot more detections of PAHs at high distant objects, high redshift objects. The PAH-SFR relation that I showed you earlier does evolve with redshift, and we have to keep this in mind, as is shown here from the work of Shipley et al. However, it has been calibrated for the appropriate redshift. I think this can be used, the PAHs can be used to detect SFR, star formation rates. And again, what I showed earlier, but whatever observations we have from Spitzer in higher redshift, so around redshift 2 basically, and I think at the redshifts higher than 2 we have stacked data. Again, we see the same thing that we noticed locally, whereas at lower metallicities, the start from the luminosity of this molecules is, or the strength of the emission bands is reduced. Right, so now I'm coming to reviewing what is happening or what we know about emission from PAHs in active galactic nuclei. Now, I should say right from the beginning, PAHs have been detected in AGNs. There are loads of papers. I have listed some. Apologies if I have forgotten to list your favorite paper, but there are plenty of detections of PAHs in AGNs, in CIFAR2s and CIFAR1s, so they do exist. However, we know now, and later on, I will show quite convincingly that the AGN does actually influence the emission of the PAH in those objects. So here is a collage of various spectra, IRS spectra, and you can see here the blue bands denote the location of the most prominent PAH bands that you can see here. And I've also shown NGC 4151 as an example of an AGN that doesn't have PAHs. So for AGNs, you can actually go from things that have, you know, emission, quite strong emission in all the bands, the mid-infrared bands, to objects that are flat, as we call them. And although disappointing, this is also giving us information about the properties of the dust in these objects and of the influence of the AGN on the dust, we hope. Now, do PAHs get destroyed by AGN emission? I should say here that up until sort of maybe 5-6 years ago, or even more, up until 2010, I think that the prevalent notion was that, yes, the PAH actually destroys, the AGN destroys the PAHs, mostly because, especially the smaller ones, mostly because we know that the very small grains suffer sublimation or sputtering. Basically, they are destroyed in the presence of very intense radiation fields, such as those encountered by AGN. However, a concerted observational campaign with CanariCam in the Spanish Gran Tecan 10-meter telescope showed that this actually may not be the case, or it might be the case, but it's not it's not something that holds universally. And here I show a couple of spectra from the work of Almudena, Alonso Herrero, and Cristina's, Ramos Almeida, where they have used the 11.3 PAH, and this is ground-based now observations. And from the ground, we can only access the 11.3. The other features fall into parts of the atmosphere that we cannot observe from the ground. Where you can actually see here, these are locations away from the nucleus. So nucleus is 0, the N not denotes the nucleus. And then the other positions are positions where spectra have been taken, and you can see them on the plot here on the right-hand side, where you can actually see clearly the 11.3 feature. So what I was saying earlier, that, you know, very close to the nucleus, what we thought was happening, that the dust is destroyed, therefore the PAHs are also destroyed, might actually not be true. We do have evidence now for emission, PAH emission, from very, very close to the central nucleus. And in fact, I'm going to go a step further and say that, well, it may well be the case that the PAHs are excited by the AGN. Remember a couple of slides ago, I said that the PAHs are excited by UV photons from the photospheres of stars. And this is why we have been using PAHs to trace star formation. However, in a recent paper by Jensen and collaborators, they make the case, and they actually support it with their analysis, that the photons that excite the PAHs may actually be coming from the AGN. Now, again, this is something where I think future observations with JWST will be very decisive, whether this is indeed the case. But if this is actually proven, and we can discuss about this afterwards, of course, it will have implications for the use of PAHs as SFR tracers. On the other hand, it will be another very good diagnostic for the properties of the ISM in AGN. So why did Jensen et al. Make this statement? This is a plot of the PAH luminosity, and I repeat again, this is based on 11.3 measurements as a function of distance for the nucleus for a number of galaxies for which they have data. In this plot here, what they have done is that they have normalized. They take the surface brightness of the PAH, and on the x-axis here, they plot the distance, the sublimation radius, so the distance from the nucleus. And what they find actually is that so all of this is within up to the sublimation radius, and the hatched area is above, I think it's above 5,000 R sublimation. And on this part, the hatched area, this is where the emission, the PAHs, the 11.3, is actually excited by star formation, because it's far away from the nucleus that there is not much chance for a photon that was emitted by the AGN to reach and excite PAHs. However, before that, in this region here, they find that actually most of the slopes, if you exclude this one, which is Circinus, most of the slopes for the other objects have the same slope, and based on that, they make the suggestion that there must have, so the PAH emission must have a common origin, and their speculation is that that may be photons originating from the AGN. Again, this is something worth discussing perhaps later on, but it is a viable suggestion. It is a possibility. Right. Okay. So moving on from AGNs onto PAHs and the ISM, and in particular PAHs and CO emission. Now we know that from work with Spitzer and ground-based measurements of CO, that the two actually follow each other. And you can see here in the maps, this is PAH emission in the middle, and so I think the contours are, the underlying is the PAH emission, and the contours on top is CO emission, and you can see a pretty good correspondence. And this is not surprising, right? Because, PAH is growing PDRs, CO also grows there in the gas industrial mix. So it is natural that the two should agree. Now, to test this further, we initiated a project to actually take measurements of CO in a sample of relatively local out to 0.3 galaxies, the 5 new sample, for which PAH measurements were already available. And you can see here the plots of infrared luminosity for all the sample, and the strength of the 6.2 on the left-hand side, and on the right-hand side, again, the same with the CO. And you can see pretty good correspondence, basically, between the two. Such a good correspondence that led the authors of the paper, Kordzin et al., to propose that PAHs can, in fact, be used to trace molecular gas mass. Again, based on this plot. You can see that there is quite a bit of scatter in this relation, but again, over 2-3 orders of magnitude, this correlation seems to hold. And again, on global scales, because don't forget, these are global scales, so the CO measurements include the entire galaxy, the PAHs again, this correlation seems to hold. Now, what happened in sort of scales, resolved scales, is a different matter. And whereas we have the ability to trace what happens with CO from ALMA measurements, we don't have the same ability for the PAHs until and unless JWST flies. But again, this is another area where we think there will be a lot of interest and a lot of exciting new results that will come out. Okay, so this was all as a review of what has been going on with the PAHs and the various ways that we have used them to diagnose star formation, ISM, grain properties, the whole lot, even AGNs. But what can we learn about PAHs and their spectrum? So to sort of get a better feel of what we can learn from the spectra themselves, a couple of years ago, with colleagues in Oxford, we decided to look at developing spectra, spectra ourselves, at computing, actually, I should say, theoretical spectra of PAHs ourselves. Now, to do this, this is far from easy. It amounts to solving basically Schrödinger's equation in order to determine the frequency of the molecules for a complex, for a molecule with, many molecules, many carbons. Now, this is far from trivial, and as you know, Schrödinger's equation can't be solved exactly for anything that is not a hydrogen-like system. Lot more for systems that have n number of carbons and hydrogens around them. So to make the analogy with the hydrogen nucleus and the electrons around. So you need approximations, and chemists have a lot of approximations up their sleeves, which I just sort of list here. But for most of our calculations, we use the density functional theory. However, from a point on, when the molecule becomes very big, even that becomes an inadequate approximation. Now, in these calculations, what do we try to get? So we try to optimize the geometry of the molecule in such a way that the potential energy surface is at a minimum. So basically, we are trying to sort of set up the geometry in such a way that this potential energy surface, which is the point I illustrate here, the blue point, is actually at a minimum. At those points, we can calculate real frequencies, because if you solve it for any kind of configuration, you will end up with imaginary frequencies and real frequencies, and we are, of course, not interested in the imaginary frequencies. To do that, we use a basis set, which is a set of mathematical functions that represent these molecular orbitals. And these orbitals are expressed as linear combinations of these mathematical functions. As I said earlier, for the frequencies of the spectra, we are interested in real normal mode frequencies, not imaginary ones. And once we have identified these lowest energy points, at those points, we estimate the frequencies. Now, the molecules that we've put together, they've all been done using Gauss View version 5. And most of the calculations, again, not all, have been done using Gaussian 09. And these are the functionals that we have used which I just give it here for those that are interested. And we have always tried to find a good compromise between accuracy in the spectra that we get and also speed, because these are very complex calculations and usually run for days and days. Okay, and the harmonic frequencies that we have calculated comes both for neutral and for cationic molecules. Now, here are some of the molecules that we have developed, and currently we have developed PAHs that go up to 1500 number of carbons. I should say here, of course, that NASA Ames, they have for many years assembled quite a large database of PAH molecules. And we have also used that database in our work, but the database there is limited up to about 400. And we wanted to sort of see what happens when you put together, how the spectra look when you put together large molecules. And at the moment, we have gone up to 1500 carbons. Some of the spectra are shown at the bottom. Now, why are we doing this? Okay, so the goal of our project is to establish how the size of the molecule, its ionization state, whether it's neutral or ionized, or the hardness of the radiation field. I'll come back to this. The geometry and any possible heteromolecules, and this is what I mean by substitution, can affect the strength of the feature. So when we get our PAH spectrum from JWST, from Spitzer, why do the bands have different strengths? What can we learn from that? Now, I should make a point here, and I should actually stress that what we get out of the models are actually the frequencies of absorption features. And we actually need to multiply the spectra with the emission model. Imagine it as a kind of a black body to get the emission spectra that we see from galaxies. And if you want more details on this, please do ask me afterwards. And we have various tools and various ways to basically do this multiplication of the absorption spectrum to get it into an emission spectrum to be able to compare them further with the observed PAH spectra. Okay, so this is the goal. This is the reasons why this project was started. Okay, so what did we do next? Then, in order to be able to see how the various bands behave for various number, originally we started by trying to figure out how the size of the PAH may affect the strength of the bands, how strong each of the bands is. And in order to do that, we used part of the molecules we have developed ourselves and part of the molecules from the Ames database, and we actually bind them in number of carbon size, and we looked at the cumulative relative intensity, basically the intensity of each band as a function of the number of carbons. We did that, and this is, we looked at the band ratios, and I show here on the left-hand side, the 6.2 over 7.7 and the 11.3 over 3.3. We did a lot of combinations. And we can see that both of them can actually track the number of carbons. However, when we looked at how the radiation field, the strength of the radiation field, so this is the energy of the photon that is absorbed by the PAH molecule that is then excites the PAH molecule. Okay, how the ratio relates on this, and this is what I plot in these two plots here, and you can see that there is a bit of a more dependence on the strength, on the energy of the photon for the 11.3 over 3.3 ratio, and this is what we found. Okay. We also looked at how now the hardness of the radiation field influences the ratios, both for small and large molecules, and you can see the plots here. And we also looked at how the fraction of neutral versus ionized molecules affects the ratio. Now, these are just a couple of representative plots. We sort of looked at other line ratios, but we found that these are sort of had the best diagnostic value. Now, by comparing all of this, we managed to put all of these grids together. And for both, the top one is for neutral molecules and the bottom one are for ionized, for various, and we examine various line ratios and various conditions, okay? So all of this was theoretical. And now when we go on to putting some data into our plots, this is the first sort of grid. I'm going to show more grids than this. What we find here, these are the galaxies, the various colored symbols are various types of galaxies, H2 galaxies, Siffords and Liners and dwarf from the SYNC survey. And you can see that, yes, sort of the galaxies cover the entire range. There are galaxies which are also outside of the grids. There is a variety. So do these grids help? Well, I think they do. They do allow us to find out a little bit more about the properties of the ISM and the properties of the dust grains in these galaxies. This is a plot from the paper of my postdoc Ismael Garcia Bernetti, where he looked specifically at AGNs. And the colored plots are color-coded, the color symbols are color-coded based on AGN fraction. The stars are normal H2 region galaxies, and you can see that they sort of span a wide range of properties. And in fact, we have a lot of objects here out of the grid where we think, that's why we think we need the large molecules that I showed you earlier, because they will be able to account, we will be able to account for these points here. Okay, and we proposed a 3D plot which gives, which combines the strength of all these features, which will be observed with JWST, and one will be able to infer the properties of the ISM. Now, I would like to sort of show a little bit more of our work. We have also been experimenting with substitutions, with substituting one of our carbon atoms in the molecules by nitrogen. And this relates earlier to what I was saying with the substitutions and eventually with the metallicity. So we looked at substituting 1 carbon, 2 carbons, and 3 carbons with 1, 2, and 3 nitrogen atoms. And we experimented with the coronin because it's a small molecule. And you can see here on the right-hand side how the spectra change, how the strength of the bands, of the PAH bands actually change. So we think there is actually a viable way of pinpointing abundances using this. And again, you can see here how the shape of the 3.3, the profile, the line profile of this feature changes depending on whether we have 1, 2, 3 nitrogens in our molecule. This is now the spectrum underneath is the spectrum of NGC 7027, which is a well-known planetary nebula, which has been observed with UKIT at a relatively high resolution. And we try to match the spectrum by having three nitrogen substitution actually. And what I would like to draw your attention to are these points here where you can see the arrows, which are the overtones at 3.4 and at 3.5. And depending on this substitutions of carbons with nitrogen, so if you take away 2 carbon molecules, 3, and substitute with nitrogen, gives rise to this sort of overtones here. And this we think is a viable way of pinpointing this issue with the metallicity that I mentioned earlier. Now, very quickly, the other point that we are interested in figuring out more is what happens with dissociation of molecules. We know that the PAHs are stable molecules. However, if you bombard them with photons of very high energy, you can destroy them, dismantle them, you can dissociate them. However, it is, I think, well known by chemists that PAH molecules, before they sort of they are destroyed completely, they will try to dissociate, they will try to keep their stability by cutting out, so to speak, either a single atom or the C2H2 acetylene element in order to be able to keep the stability. Okay, so is this the case? If this is the case, if in fact, high radiation doesn't actually fully destroy the PAHs, but makes them, reforms them into something smaller, could that be interesting to sort of understand what is happening PAHs and AGNs? Now, we have again tried with our modeling to look at this. So we have actually tried to tear apart, open one of these benzene rings, okay, and you can see here, and you can see how the spectrum again changes. And the blue is what I call the coronine ragged, which is the last molecule here, where via chemical pathway, we managed to break apart the bond. And you can see that the spectrum actually changes. So we do think that something similar may be happening with the AGN, in the sense that the very hard photons that are hitting the PAHs may be tearing the PAHs apart, and then you have the different line ratios. Now, again, this is work in progress, but I think it's sort of is a demonstration of what I was saying earlier. So this is the grid I showed in my earlier slide, and this here, the colored, are the points from the spectra that I showed before, where we were looking at the dissociation of these molecules. And if I put the same kind of galaxies that I showed earlier, you can see that we are now we are approaching sort of the values that we see in these dwarf galaxies. As you know, in dwarf galaxies, the radiation fields are very, very hard, very intense. They are fairly smallish galaxies. The PDRs are small, but they experience a very, very high radiation field. So we think probably this might be happening in dwarf galaxies and perhaps in AGNs as well. We also look to see if we can find differences between central AGN emission and circumnuclear, nuclear and circumnuclear. And again, this is from Ismail's work, where we have taken Spitzer IRS spectral maps and tried with a lot of effort to distinguish between or measure nuclear and circumnuclear regions. We were hoping for a nice correlation. We were hoping that the nuclear points, as you can see, the stars are the extended, the circumnuclear, and the air or the circle are nuclear, depending on whether it's a Sifert 1 or a Sifert 2. We were hoping to see, the 6 points in one direction, but that's not happening. This could be due from the fact that the Spitzer spectra are, of course, the resolution is very limited. but it could also be happening because hydrogen has a role to play. Recommend, if you're interested into this, look Almudena Alonso Herrero's recent paper issues of whether molecular hydrogen plays a by shielding these molecules from the radiation. So again, this is another area where now the combination of ALMA, where we can measure an infrared will be able to help, and we will be able to distinguish one way or the other, understand better the role of H2. So I think I'm going to stop here. So we have embarked on a project to understand the properties of PAH emission from space using chemical networks. We have identified some ratios which could be used to probe molecular size, fraction of neutral versus ionized molecules and grains. Some of this is work that was done before with Train and Lee back in 2001 with a slightly different method, so we confirmed these results, and others. And then we also looked at what happens with inactive galactic nuclei and whether these molecules that are very close to the ionizing source can actually be ripped apart. And what is the role of molecular hydrogen in those systems? Now, the geometry, as I said, is important, as are the heteromolecule substitutions, because they might give us an avenue to address the issues related to the metallicity abundances. Spectral and spatial resolution are both key, and I think it doesn't need stressing that observations with James Webb will be revolutionary to our understanding of PAH molecules and other issues, of course, much like ALMA was for molecules, for the extended molecular network that has been identified. So JWST will sort of bring a similar kind of jump in our understanding. Understanding PAHs at the smallest scales is very important to understand PAHs, of course, and this is important for this kind of surveys that have been designed. A lot of great science is to come, and I think I'm gonna stop here and say thank you.
Thank you, Dimitra. Any questions?
Oh, wow.
Okay, while people are thinking and building up the courage to ask their questions,
please do ask me questions.
I'm wondering, do you see any regularities on the sites where you have this indication that PAHs are ionized versus where you see them being neutral? Do you see any regularities there?
When you say regularities, what do you mean?
I mean, do they correlate with the type of galaxy or the location and so on?
Yes, they do actually. They do. But it's very hard location-wise. We can't say much because we don't have spatially resolved data. So it is hard to say, but I would expect that yes, they do. There will be some correlations, but as I said, it is very hard for me to be able to say that location-wise, we tend to find, but that's based on unresolved data, that star-forming galaxies require more PAH, more ionized PAHs than neutral ones, than AGNs or normal galaxies. This is what we have found from our diagnostic diagrams. Spatially wise, I think this will probably be able to answer after we get some spectra from PAHs from JWST.
I see, thank you. So we have one raised hand from Jason. There you go.
Hi, great, thank you very much. I'm not quite sure, maybe right at the end you answered this, but I'm not quite sure.
Yeah.
So molecular hydrogen, one of the big questions I understand, it's, as you know, it's not my field. One of the great questions in molecular gases, since we measure CO and we have this alpha parameter that we go to H2 with, this is a magic number that has proponents and religious validity at some point. So the puzzle I had was, since H2 also forms on dust grains and the PAHs are in a sense more readily detectable, is there a way, and is this what Almudena in a sense is working on, of tying through the CO, because you're seeing CO, you have the CO and PAH maps, is there a way to tie that into a bound on alpha?
Well, difficult. I mean, so in the paper that I showed, the result that I showed, Isabella's, the Corset paper, where they use 6.2 to get masses, yes, but you're going to have another alpha. You're not going to get rid of some conversion factor because you go in directly. But there is a but there. JWST will be able to detect H2 directly, the mid-infrared lines. So that might be a way out, because we will have, that might be a way out to pin down this conversion. I hope, I very much hope. I mean, you know, back in my youth at MPE, we tried to do this business with looking with H2 from ISO data. Did we get anywhere? We have, you know, few data, but that might be the only way to actually pin down the conversion factors. Yeah.
Any more questions? So there is one from Vasilis.
Yes, Dimitra, this was a great talk. A couple of questions actually. One, you mentioned about the usage of 11.3 micron PAH and how this may be destroyed by AGN, right? No, excuse me, no, that this may be present in AGN, the work that Almudena had done, right? And we had seen that even way back with ISO, with in the spectrum of 5195, remember, where you could see the 11.3 and there were arguments that this is a liner galaxy, and then maybe you see it, right? But so the question is there something special with 11.3?
No,
and if we see it in the 11.3, why does the 12.7 disappear, or the 7.7 also goes down?
The work also... with the plots that I showed with 11.3, as I said, this is only because this is what CanariCam can observe.
Okay.
So they only have measurement of that particular feature. It's not to say that the others are not there. It's just that they have done a lot of work based on that because that's what they have, spatially resolved.
I see.
So, no, there is nothing special about 11.3. I mean, there are special things about 11.3, but there are special things for the other features. So the answer is no. There's nothing special. And again, what I'm going to say is that, you know, we need JWST because we need to see spatially resolved all of them, not just the 11.3. And in fact, I should say here that one of the difficulties with these observations, the CanariCam, is that the continuum is very poorly defined.
Yeah,
and yes, there is a lot of work that the team have done, and I think is actually quite interesting. But the determination of the continuum underneath is very, very difficult. So, no, I mean, you can do it with any. It's just that that's what they had.
And the second question is, you showed all your new work, right, with the simulations increasing the number of carbon atoms in the PAH molecules going up to 1500, right? So to me, maybe you already do that, right? But in these simulations, right, there are some assumptions in the PAH molecules, the fact that they remain planar, right? And or whether you will have impurities introduced in the grid, right? So when people do this type of, first of all, do we have real evidence in space that such large molecules actually do exist? That's a more generic question, right? When you simulate them, do you take into account of the fact that you're not going to have a flat, you may not have a flat, but it will start bending, right, and folding?
We don't. I mean, I think the largest molecule are the fullerenes, C60s. Right. So, but what we see from the grids, and that's not just, this work, this was known from before, we do have larger, there must be. So the assumption is the following: if PAHs grow on grains, and the larger the grain, we can afford the larger PAH. So you need to have, and if you need to have a large enough range to see where you might be. As I said, we don't know because we've only sort of identified the fullerenes. JWST may identify larger. On the geometry, the reason why we have these planar structures is that these are easier to calculate. These take about a month each to do the calculations on supercomputers. So you can, once we have this structure, then we can start building something, a 3D, whatever you want. On the impurities, if by impurities you mean substitutions, right, is that what you do? Without that, we control, and we can put, whatever we want in there. Basically, it is a parameter that you can control in your model.
Okay, thank you.
There is one more question by Mario Salamidis.
Okay, so thank you for your presentation. What about the PAH molecules' presence in our own galaxy, even our own solar system, and what can this tell us about the early stages in the life of our own solar system? Thank you.
That's a very good question, but I'm afraid I'm going to decline, or I'm going to ask anyone from the audience who is a solar expert or a solar system expert. I cannot answer this question. I mean, I'm pretty sure you can use them, as I said earlier, you can use them to track organic molecules and organic inventories of molecules in space, in the local neighborhood and our solar system. But it's beyond my area of expertise, I'm afraid. I mean, I'm pretty sure they are very helpful, they're very useful, but that's not what I study.
Okay. Are there any other questions for Professor Rigopoulou? If not, thank you again, and thank everyone for attending the first colloquium of the year, and Happy New Year again.